clear itself up a little bit. Now with that said, we've still got induction to get through. So we're going to blow through chapter 14 today. We're just hitting the high spots. But what we know about magnetic fields is that if a magnetic field is passing through a loop of conducting material, there's a flux through the loop. Is by definition a flux. If the magnetic field is changing in time, therefore the flux will be changing in time. And if that is the case, then an EMF will be induced in the coil and current will flow if that's possible. Okay, so let me just put up here a loop of current and say that I is increasing. Okay? Next to it, let me put another loop. So I've got the green loop, and I'm going to have the pink loop. And there is no current in the pink loop because of an EMF or anything that's attached to it. Let me just ask you this. If there's a current in the green loop that's increasing, is there a changing flux through the pink loop? Yeah, sure. It's not a trick question, right? I is going to produce a magnetic field. Now, we've talked about the fields of loops. And normally when I would draw this, I would draw the field right there, right? But remember, that is true only at the direct middle of that loop, right? And that's what we've been focusing on. But every part of that wire is producing a magnetic field. And as you get out from the center, it starts to form loops around the wire, right? And so absolutely this is producing a magnetic field, which is passing through this loop, right? And if the current is changing, if I is increasing, is the flux through the pink loop increasing? Yeah. So will there be an EMF and hence a current induced in the pink loop? Yeah, absolutely, right? This is called mutual inductance. And your book goes into it much farther than this, but this is as far as I'm going to go with it. I just want you to know that it's a thing. Why do we care? Because some of you are going to be dealing with breadboards at some point in your life, right? Even if you're not double E. Very often there's electronic things that happen in all branches of engineering, right? So if you don't know what a breadboard is, I think you've been through enough labs at this point to know what it is. It's a board on which you lay out different circuits or different parts of the same complex circuit. And so if you have a circuit on a breadboard and then another circuit right next to it on a breadboard, this is something you have to be careful with, because if you run some current through one of your circuits, then just de facto you get current in your other circuit whether or not you like it. If there's two currents running, they're going to affect each other. There are ways around it. You can electrically shield them from each other, things like that. But it is something that you have to be aware of. Just the physical proximity of two circuits leads to mutual inductance in the circuits. They affect each other. That's as far as I'm going to go into it. There's no math to do here. See your book for details if you want to, but I'm going to move on to something else. I just want you to be aware that this is a thing. Okay? My background is in music and the sound industry. Before physics, I did a lot of stuff with music and sound. And if you've ever seen a soundboard, right? Things they use to either mix music live or record music. I mean, the old school ones where they were actual physical. It's basically a collection of circuits lined up next to each other. Sometimes 8 on the smaller ones, goes up to 64 or 128 on the really, really big ones. So it's circuit. And when they first started using these back in the 60s, they had a lot of trouble, which was called with what they called crosstalk. In other words, stuff happening on this channel. So you might have a guitar run to one channel, and a singer run to the next channel, and maybe a bass guitar run to the other channel, whatever. Right? Well, what the guitarist was playing was coming into the board, and because these circuits are right next to each other, you would start picking up stuff on the next channels over. It led to a lot of problems, so they figured out how to isolate the channels, right? But this is something that happens in the real world. It's something you have to be familiar with, this idea of mutual inductance. What happens over here affects what happens over here. You can't really get around that. Okay? Especially today, because electronics are going smaller and smaller and smaller, right? So you have closer and closer proximity, so you just have to be aware of how to handle it. That's another class, but I want you to be aware that it's a thing. That's mutual inductance. What we are going to go into is something a little bit more complex and maybe a little bit more interesting. Okay, I've erased the second loop. Let me ask you the same questions. Is there a flux, a magnetic field flux, through that green loop? Not a trick question. Is there a field through it? Yeah, then there's a flux. Now, where's the field coming from? It's coming from the wire itself, and that might strike you as a little strange that we're worried about something that the wire itself is producing, but this turns out to be a thing, right? The wire is carrying a current, which is producing a magnetic field. That magnetic field is passing through this loop. Therefore, there is a flux through the loop. Is the flux changing? Is the current changing? The current is the source of the field, therefore the source of the flux. Is the flux changing? Yeah, the flux is changing. So, will there be an induced EMF? Yeah, there will be. So, assumedly, I haven't drawn it, there's some constant EMF that's producing this current to begin with, right? What I'm saying is, in addition to that, there will be a further induced EMF just because of the fact that this is a coil, or a loop, however you want to call it, carrying a current. Therefore, there's going to be a magnetic field, magnetic flux, changing magnetic flux through this loop. So this is called self-induction. And it's also something that you have to contend with, right? To characterize this, I'm just going to get into this a little bit. Remember Faraday's law. N dV dt, right? This is Faraday's law. The induced EMF is equal to the negative time derivative of the magnetic flux times however many coils of wire you have. Right? So this is something we know. Let me write it in maybe a simpler form, right? The induced EMF, just by virtue of this law being true, is proportional to the change in flux, right? This is the mathematical symbol for proportionality. It looks like a little fish, or at least it's supposed to. Mine doesn't really, but this is proportional to the magnetic flux. Now, where's the flux coming from? What's producing the flux? Well, the field, okay. What's producing the field? The current. So I don't think it's an unreasonable step to say, well, what that means is that the induced EMF is proportional to the current that's flowing in the wire. Right? What I'm recognizing is that in phi is buried I, and so if it's proportional to phi, that is proportional to the change in phi, it's going to be proportional to I, right? That's what's changing in the first place. Does that reasoning make some sense? All right. So we now have a mathematical proportionality. How do you turn a proportionality into an equation? Anybody know? You run an experiment and you determine the exact quantity that makes this proportional, right? We don't really teach that a lot, and it's a shame we should. That's how physics proceeds, right? We figure out that something is proportional to something else, right? You can do that just by thinking about it. The force of gravity is proportional to your mass. Well, how exactly is it proportional? Well, to do that, you have to run an experiment, take data, and come up with what's called a proportionality constant, right? It could be called whatever you want to. You've seen them in your entire physics career. Just people may not have called them that. But that's what you do. You take this proportionality, you run an experiment, and then you take data and you figure out exactly how it's proportional, and then that allows you to turn this into an equation where this is just a letter that I chose, L. I chose it because your book chose it, right? It's just a letter that I chose for the proportionality constant. Of course, different experiments on different materials, different situations would yield different proportionality constants, and that's fine. This is standard procedure of how you turn a proportion into an equation. You find the proportionality constant. So you can still say that the induced EMF is proportional to the current, but it's exactly proportional through the proportionality constant. In this case, I've called it L. L is called the inductance. It's the inductance of a particular circuit. Again, it's going to change depending on your circuit, but it is a thing that will be able to characterize all circuits. All right. So now that we know what that is, well, okay, this is one way. This is how we figured out that it's a thing. Yeah, that's as far as I'm going to go. Your book goes, like I said, goes a little farther. We're in speed mode, and there's lots of things in here that are needlessly complicated. If you need them in future classes, you'll get them at a much deeper level. So we're just going to leave this here. The inductance of a circuit is this proportionality constant, right? So I should point out, you've seen something similar to this. Right? Voltage is proportional to current. I think we'd all agree that that's the case. How exactly is it proportional? Well, you run an experiment, and on some particular circuit, you come up with that it's proportional to some constant, which maybe we'll call R, and then you get Ohm's law, right? It's the same sort of idea that we did here, right? Where R is a physical characteristic of that circuit, and L, or that piece of a circuit, and L is a physical characteristic of this circuit or this piece of the circuit. Does that make some sense? Right. Both of them mitigate how the current flows in response to a voltage or an EMF. All right. Although this takes into account the resistance of the wire, that takes into account the loopy nature of the wire, if you will. All right. So I wanted to put Ohm's law up here because we also developed some notation for dealing with this. For Ohm's law, we said, okay, well, what if I have a circuit and I recognize that there is resistance in that circuit by drawing a symbol? And you remember what I said this symbol could mean? This could be a particular component that you put into your circuit to increase the resistance. It could be a particular component that you put in to do something that has resistance, like a light bulb, right, or a motor. It could be just a representation of the fact that this wire itself has resistance. And so that was sort of the model we got. We assume that our wires are resistanceless, and we wrap all up their actual resistance into some symbol. And then after we do that, we don't actually have to care about whether the wires are resistanceless or not, right? This represents either a component or the resistance of the wires themselves, okay? Right? Does that make sense? We can do the same thing over here. Recognizing that every circuit, by the fact that it's a closed loop, otherwise it's not a circuit, has inductance. We can develop some terminology for that. So what did I draw? I just drew a coil, right? So it turns out that the same thing happens here. There are coils that you can put into a circuit. They're called inductors, just like there are components you can put into a circuit called resistors. If you ever opened up a circuit and seen a coil of wire lying on it, that's an inductor, right? It doesn't have to be a component. Every circuit has inductance by virtue of being closed. So this symbol could mean a component. Could just be a shorthand for the natural self-inductance of the circuit, just like the resistor, okay? Does that make some sense? All right. So now we have another electronic component. We're not going to go into parallel and series stuff with this. We're just basically going to talk about what it does for you, okay? So let's, if we any questions about any of this before I erase and draw some other stuff? All right, then let's set up a system and talk about what would happen if we allow this system to evolve. And remember, this is all self-inductance. All right, under that umbrella. I'm just going to start with this. I'm only going to draw a part of the current. So, clearly, there's other parts of this circuit. It has to connect, or it's not a circuit, right? I'm just going to draw a part of it. And I'm going to say that when we're looking at it, my current is steady. In other words, not changing in time, right? So it's moving, or I should say the charges are moving, the current is flowing. Let's ask ourselves a question. Is there a magnetic flux through this coil? Is there a current?
Yes.
Yeah. Then is there a field? Yes. Then is there a flux? Absolutely. Not a trick question, right? What would that look like? Well, we know what the magnetic field due to a solenoid is. It's basically what this is. It's not functioning as most solenoids function, but that's basically what it is. It would look something like this, right? So there's my B field going right up the coil. Is the field changing? Where's the field coming from? The current. Is the current changing? No. Is the field changing? No. I'm leading you in the steps purposely. These are the questions you should ask yourself, right? So, no, the field is not changing as long as the current is not changing. Therefore, is the flux changing? No. Therefore, is there an induced EMF in the coil? No. Right. Okay. Well, what happens if I turn off the current? Right? So my current is flowing, and then I flip a switch, and the current is trying to stop. Let's ask ourselves the same question. Is there a flux through the B field? Well, at the nanosecond that I flip the switch, there's still a current flowing. So yes, there is a B field through the coil. Then the current tries to stop. It tries to drop. So therefore, is the flux going to change? Absolutely. Now, will there be an induced current? Yes, an induced EMF, induced current. So what is the flux doing if I turn off the current? Is it decreasing or increasing? Decreasing. What does nature want to do? Increase it. In what direction should she induce a field to increase the flux?
Same way.
To increase the flux. That way, right? That's the field that already exists due to the current flowing. If you shut off the current, nature needs to boost up that field, right? So she has to induce a field this way. That means she induces a field, or she induces a current that flows in the same direction as the current that was flowing, right? In other words, nature tries to keep the current flowing. Right? She doesn't succeed because things get turned off, right? If you don't believe me, here, I'll do it, right? It actually happens, but she gives it her best, right? So she induces a field, I'll do that in blue. She induces a field this way that has to come from an induced current flowing like that. Now, again, she fails, but she tries. But as the current falls, well, she can induce less and less. But the upshot of this is that if I graph the current as a function of time, right, where this is my steady current with which I began, right? This is, we'll call it I naught, just to differentiate. And then if this is the point where I flip the switch, the current starts to drop, but the point is it does not cease immediately. It starts to asymptotically approach 0. And of course, mathematically it's asymptotically. Physically, it actually gets there. Right? So there's this region of time in which after you flip the switch and shut off the EMF, you still have current because of the induction of the circuit, either an inductor component or this is a natural self-induction component. So you have this decaying exponential. Where have we seen this before? What were we talking about when we saw a current decaying exponentially? It hadn't been that long. Where did the current decay exponentially when we turned it off? Discharging, does that ring any bells? You do have a final exam coming in. I should point that out. You shouldn't forget these. This is like a discharging capacitor. Right? This is exactly what the current flowing out of a discharging capacitor looked like. It flowed robustly at first. Well, this wouldn't be in a discharging capacitor, right? Because there was no current flowing at first. But from this point on, it flows very robustly, but as the charges get off the capacitor, it asymptotically approaches zero. Right? So this makes the circuit actually behave somewhat like a discharging capacitor. So all this to say is you will never have a situation where you can cut off your current in a hard step, right? You can get close. You can get this time really, really slow, or sorry, really, really fast. But there's always this exponential nature, just simply because of the self-inductance of the circuit. Now, let's ask ourselves another question. What happens if I have no current flowing? I have no current flowing, but then I turn on a switch and the current tries to start flowing. So ignore the green arrow. Before the current flows, is there flux through the coil? Definitely not. There's no current, there's no field. As I flip the switch on and the current starts to flow, is there a flux through the coil? Yeah, so it was no and then it was. So that's a change. So there's a changing flux. Nature tries to induce, or not tries, she does induce a field to counteract a change in flux. In that case, right, if the current is flowing, if the current starts to flow to the right, nature is going to induce a field that tries to stop it. That'll look like this. Again, she fails, but she tries. So what this means is that if I graph the current now, it looks like this. Right? Nature tries to oppose it, but the current builds up anyway, asymptotically approaching its final value line. Now again, this time window is probably really small. I mean, you can see it yourself. If I turn off the light, it goes off pretty quickly. If I turn on the light, it comes on pretty quickly. These are a little sketchy because you also have the time to get the to excite the atoms in the gas and the fluorescent bulbs. But you see the idea, right? It's really quick. So this is a usually really quick time, but it's not zero. You never get hard edges on these currents, turning them on or turning them off. This looks a lot like a charging capacitor. All right, so there's lots of similarities going on here between how circuits act. Whether or not they have capacitors or not, you will get this sort of effect just because of the self-inductance of the circuit. Questions about any of that?